Good day, I'm Dr. T. Welcome to my office, and we are talking about measurement. Okay, so starting out the video with a little bit of further reading. In this case, it's going to be further viewing. I'm really a big fan of Joseph Newton's Cursed Unit Trilogy. It's a series of currently 3, hopefully more. I love these things. Going over just weird units. And some of them are not as weird, but they're weird when you dive into them. So I encourage you to check that out. That's a fun view. Okay, so the module is going to be over measurement, density, data analysis, that kind of stuff. And of course, this video series is in support of an education course. So I actually want to take a side, and I'll get to the science or the metrology, which is the study of measurements. I'll get to the metrology here in a little bit. But I want to take a little bit of a detour to Johnston's triangle. Okay, so Johnston's triangle is an idea of teaching chemistry. And it really applies to other sciences, though. Definitely biology, geology, a few others. But it's set up in the chemical education literature. And so the idea here is that the world that we see, the macroscopic world, the world that we experience, in order to understand that, we need to understand it at a couple other levels. And first is the world of the very, very small, the atomic or the molecular level, or in case of something like biology, the microscopic level. And by understanding that, we understand the macroscopic world. The classic example is if you are, say, splitting a log. If you go with the grain versus against the grain, it's profoundly different as far as cutting it goes. And that, of course, is the direction in which the cellulose strands go. If you're splitting a log and you're splitting it apart with the grain, then you're ripping cellulose apart. But if you're chopping the log, then you're going and cutting the actual cellulose molecules. And it's the difference between relatively easy and a lot more work. You need a really sharp axe to do it, chopping a tree. So that's one point. And we'll get there. That's the next little bit. But the other point on Johnston's triangle is the symbolic or the numeric. In order to understand the world around us, we generally have to convert that into math, because we're going to understand how math works. In the previous video, I talked about models and how a model is our conceptual framework. The model is almost always an equation. It's not always an equation, but it is often an equation. There are by far more equations for models than otherwise. I mean, even if we're talking something like AI, an AI model is basically a gigantic mathematical operation. We're converting language into numbers. So in this case, we need to do that whole conversion into numbers. Now, we're not converting language into numbers. This is not LLM class. This is physical science. So we're going to deal with things that, are things you can hold and turn those into numbers. And this becomes the field of metrology. So I want to introduce this idea. And of course, the goal here is, if I just have, a fish, I can say, hey, fish. I should have had an example of a fish. I don't, but you get the idea. But of course, if I'm telling you about the fish and I don't have the fish with me, I have to say, well, the fish was this big. Yep, the fish was this big. I caught a fish this big. And so now I can tell you, but if I'm not with you, or I need to write it down because for some reason you don't believe me that maybe each time I tell you the fish was this big, you think it's larger. I don't know why. The fish was always this big. Well, in that case, I need to convert this into an actual number. And there's a bit of a problem. It's a fish. So I need to say the length. Well, how do I say the number for this? What is this number? I can put a number on it. I can say 42. But that doesn't mean anything. Of course, that's the gag in the classic science fiction work, The Hitchhiker's Guide to the Galaxy, the 4-part trilogy, where the computer is created by the mice in order to find the meaning of the life, the universe, and everything. And it comes back with, I have an answer, but you're not going to like it. Well, what is it? You're not going to like it. What is it? It's 42. It means nothing. By the way, if that weird set of sentences sounds good to you and you haven't read The Hitchhiker's Guide to the Galaxy, get ready for some mid-20th century British satirical humor. It's amazing. Great four-part trilogy. That's part of the joke, by the way. Okay. So a number by itself, or the value, because I'm going to contend here that a number is not just the numbers, what we normally call numbers, those are values. But in order for it to have any meaning whatsoever, it has to have context, and that context is given by a unit. And so a unit is just an idea that we've all agreed on as a society of this word or this idea, just like all other parts of language, means something. So, a foot and a half is that long. This is an 18-inch ruler, so a foot and a half. Calling that a foot and a half, though, that is an agreed concept as a society. Well, in order to do this, we all need to agree on what we call a standard, a physical object or some way of defining that unit. It doesn't actually have to be a physical object. Spoilers coming up. But we need to have some definition of what a foot is, or what a pound is, or what a light year is. So in order to do that, we need to have some definition. That definition ends up being a standard. Now that could be literally anything. Back in the day, the classic was like the cubit, which I always get this wrong, but I believe it's like from here to here. So a cubit is a length of part of your body. That's great. My fish is a cubit long. Okay, at least gets in the ballpark. Or maybe I'll use my foot. But of course we want to get things better. One of the ways of thinking about the progress of technology and the advancement of technology is really the advancement of metrology. How well can we measure stuff, and how well can we make stuff to a measure? And the better we can do that, the more advanced the technology is an argument, and that the history of technology has been an improvement in metrology. Well, we can use just about anything for a standard, but we want some nice high quality standards. And so we're going to need a couple things. One, it needs to be doing a pretty good job of measuring stuff, but also you don't want it too hard to use. You want to have something where with the technology at hand, you can get your hands on either the standard or something that's been measured by the standard, and then use that to do your weights. And to this, I always like to bring up the story of the carob tree. Over here, actually over here, I know it's all fuzzy because of the bokeh, but I'll put a picture over here. This guy is a tree. It's got a kind of a bean-like seed pod. This is native to the Mediterranean. It's a foodstuff, still eaten today. You can hit the internet and buy carob-made food. I've not had it, but but for ancient peoples, they believed, incorrectly, but they believed that the seeds were very consistent in weight. And so what they would do is if you were weighing out small items, weighing is very easy. A balance is a very straightforward thing to do. You take a stick, and you got some string and some pans, and it's easy to make a balance. We've had balances for millennia. You see references in ancient text. I believe there's a line in Leviticus about, people defrauding other people with unjust scales and how that's not cool. And so you would put the beans on one side and you would put whatever you're weighing on the other side, and so now you could balance. Now, obviously, it's not going to, you're not going to weigh a camel with a bunch of beans. That's not a great idea. You're not even going to. I mean, you might weigh a chicken, but I doubt you're going to weigh a chicken. But you could easily weigh some gold or some gems or whatever. Works quite well. And this is actually where we get the modern word carat. It has nothing to do with the root crop. And so the idea is originally the carat was the weight of one of these seeds. Now it turns out these things vary because all natural products do. The tree does the tree thing. And so later on we ended up defining the carat based off of the SI unit. It's, I believe, 200 milligrams. Okay. So we have this idea of a standard. And side note, we get the coin carat, or the carat for purity of gold, based off of a Roman coin. Basically, it's the how much gold out of 24 carats is gold. So if this coin was made of pure gold, it would be 24 carats of gold. Otherwise, it's some ratio. So we do interesting things with units that get kind of a little bit wonky. We're going to try and sort out some of the wonkiness a little bit later on. And this actually became a bit of a problem. You get a whole bunch of different standards because you're going to do things that makes sense for what you're dealing with. And so you want something that's relatively reasonable size. If I'm weighing out a goat, I'm not going to weigh out a bunch of seeds. But, I guess I could, but I probably won't. I'm going to grab something that's more appropriate to weigh a goat with. Likewise, if I want to weigh small precious objects, I'm not going to use something that's gigantic, It's just inappropriate size. And not to mention I'm going to use what I have. If I'm not in North Mediterranean, if I'm sitting over in, say, China or the New World or Africa, well, Southern Africa, I'm probably going to pick something else because I don't happen to have those carob seeds easily available. So I'll pick something that's more appropriate for my location. Well, this creates a bit of a mess because we've got all kinds of different units. All of them are slightly different. They're doing basically the same task. And we've got a bit of a nightmare sorting between these. In the 18th century, France had hundreds of units for basically the same thing. Every town had relatively similar, but not quite the same unit. And so you had to sort out this mess. Well, France was going through a bit of a period. The French Revolution, and they wisely came up with the idea of we're massive time of social change. If we're going to make any big changes, this is the time to do it. So they come up with the metric system, or I should say kind of the first metric system. And they've got this kind of cult of reason. They're trying to do everything rational. They go with everything base 10. Some things stick, like the metric system. Other things don't, like the decimal calendar. Kind of wish it did. It was kind of cool. 10 months with 10-day weeks, that kind of stuff. Oh, man, that would have been cool. Then again, it would have been a long week. So anyways, there are reasons things stuck or didn't stick. And so they come up with the metric system. That then evolves over time and becomes what we call System International for units, or I believe it's System International. They come up with the SI system, or System International. Keep in mind it's in French. And this comes into full force. The most recent update, I believe, was 2019. There might have been a minor update since then, but they keep updating and keep adjusting standards to better meet the needs of the society. But the goal here is we're going to standardize everything. We're going to use a nice set of units, and we're going to keep some units we're going to have called base units. And these are things that have a standard. And then we're going to have derived and compound units, which don't have a standard. Their standards are the base units. So, for instance, the meter is a standard of length. You do not need a standard of volume. You can simply make a box 1 meter by 1 meter by 1 meter. Boom, you have a volume, and now you have a standard for volume. You don't have to have a separate standard for the meter. And this makes life a lot easier. This is one that's going to kind of dominate global trade and dominate the sciences. So we're going to have to learn a bit more about the SI system because this is one of the major tools that we use and we have used for a very long time. There's this common joke. There's countries that use the SI system and there's countries that go to the moon. But the secret is we've actually been using in the US the SI system since before we went to the moon the first time. I guess technically the only time since we just did a lap around the moon, but you get the idea. Hopefully Artemis 4 will land here pretty soon. But I'm getting ahead of myself. I want to jump into a little bit more about the standards, and one of the reasons why we want to keep the standards down to a minimum and why we're going to make an interesting little quirk to them. But I have a bit of a story. Okay, for starters, generally, this is the purview of governments. One of the goals of governments or international organizations coming on later is to set up standards so that you can conduct trade. one of the primary functions of government is to facilitate contracts, trade, and that kind of stuff. And of course, in order to do that, you have to have defined terms. I have a friend of mine who was in law school years ago, and one of their case studies was a lawsuit involving the definition of the word chicken. Basically, was it the bird or was it a specific subset of chicken based on size? Yeah, things get crazy, especially outside of SI system. Okay, and this has been a thing. Governments creating standards of units and creating the kind of the definition of what's what has existed for a very long time. We see this in the prologue of the Code of Ur-Nammu. I'm butchering that poor guy's name. This predates the Code of Hammurabi. This is the Sumerian. Leviticus 19:35-36 references this. It's more, that was the reference from previous. It's like, it's not cool to use fake weights. It's something like, if you've got your weights for your buying and your weights for your selling, and that's not cool. You should have one set of weights. And of course, the U.S. Constitution, which is sitting behind me. You can't see that. And that's going to be Article 1, Section 8, Clause 5, which is basically the government gets to pick units. And that's one of the functions of the government. Yeah, I know. I think this is the second time I've referenced the U.S. Constitution in these videos. So this is kind of a major deal. We want to have units set. Nowadays, it's done by treaty because international trade requires international units. But there was a rather interesting one. There's a story I want to kind of tell y'all. But the British Empire, of course, no exceptions. So we're going to talk British Empire, and this is the 18th, 19th century. And of course, at this point, we're using imperial units. Side note, the things we use, the feet here in the US, these are actually based off of the SI system. They're defined based off of the meter. And these are US customary units. They are not imperial units. The imperial units are an older set that's not used anymore. And they are slightly different. Once again, there's a reason we use the SI system. It's nice having just the unit. And by the way, they've been based off of the meter since before we went to the moon the first time. Okay, so they were using the yard. The yard was their defined one. Keep in mind, a yard is about the same size as the meter. The meter's roughly 39 inches, the yard's 36. So this is a reasonable unit of length, the size of my fish. And the way they defined the yard, and this is the way the meter was originally defined, it was defined as a metal stick. And that works fine. You have a metal stick, but there's a couple of problems. One, when you're measuring the metal stick, you only have one metal stick because you only have the definition. So you've got the metal stick. I guess you could have two and you could average them, which is kind of what they did with Lagrange K. I'll get Lagrange K. But you have to measure it every time, and how well you measure it each time is always going to have a little bit of wiggle. You get a little bit of error. So you might have a little bit of random error where it wiggles just a little bit. But they had the stick, and they kept it in the Houses of Parliament. And then they'd make copies and send that out to all the towns, or all the cities, I presume. The UK has some weird things with like town and cities. In the US, it's just like size. UK, it's weird. But they've sent those to like the major metropolitan areas, or the major communities. And then those would be made copies of, and eventually you get to your local tailor who would have that stick on there, so you go, cloth cut, here's your yard of cloth, that kind of stuff. But there was a problem. The Houses of Parliament burned down, and the stick was no longer a stick. The stick was a puddle. It was never seen again. And so, of course, if this happens to you, you've got kind of a problem. The definition of a yard is now gone. There is no standard. So what they do is first to keep the big mouth shut. You don't need to go telling no one that this is not going to do good for the economic markets when they realize your entire unit of measurement, the entire foundation of trade, is now a puddle. And second, they then pull all of those original copies, so they kind of that first order copies, they pull those back, they average them, and they make a new the stick. And so the yard is now again. But that highlights a particularly big problem. That yard is a really big deal, and you don't want to accidentally lose it. So this gets back to our idea of base units. The less of these standards you have, the less of a problem it's going to be. So your 7 SI base units, these are all going to be based on some kind of standard. And ideally, you would like it to be something that can't be destroyed. Well, a thing can be destroyed. An idea cannot be destroyed. So let's go over a little bit of how they dealt with each one of these. And the most recent change was in 2019 with Lagrange. Okay, so the second ends up being like the base unit of base units. I would argue some of these base units aren't base units. They're actually derived from the second. But the goal here is we're going to derive everything from some kind of physical law of nature. This way, anyone can reproduce it. You can't like accidentally get rid of the functioning of their universe. But we start off with the second, and that is going to be a photon that's going to be derived from the frequency of light emitted from a specific energy transition, so the electron's bouncing around in a cesium-133 atom. Okay, completely random. Why on earth would we do this? Well, remember, standards are built based on what's convenient for the society. This is how legit atomic clocks work. Those $20 items you buy at the store are not atomic clocks. Those are a quartz clock with a radio to talk to a real atomic clock. Real atomic clocks have cesium in them. That's kind of what's at the core of a GPS satellite, etc. Okay, so now we got the second defined, we can use that to define the meter based on the speed of light. Basically, this really tiny fraction of a second, however long light takes to get that far, that is a meter. Okay, now let's get into the 2019. This did not make the chemists happy. The problem was the last of these units to be redefined was the kilogram. Up until 2019, the kilogram was still a physical object. These are platinum iridium orbs in France. And there was a bunch of copies. And what was realized is that the weights of the copies in Lagrange were changing. And of course, there's no frame of reference, so we don't know which one's changing. And okay, at least it's not a puddle, but that's still possible. You know, it survived 2 world wars, but it could be lost. Something horrible happened. But also, the standard is changing. That means the unit is changing. So this needed to change. There was 2 proposed ways of changing this. One was to define Planck's constant. Planck's constant on the surface is how you convert the energy of a photon to its frequency. Like, what does that have to do with weight at all? Well, it turns out it's also functioning in how a watt balance works, which is basically using an electromagnet to pick up your weight and wiggle. I believe it wiggles it. And as such, measures the mass using electromagnet. And thus, you can figure out mass with Planck's constant. The alternative was to define Avogadro's number and base the kilogram off of an Avogadro's number or a specific fraction of a mole of silicon. Obviously, the physicists wanted Planck's constant, the chemists wanted Avogadro's number, and the physicists won this time. There's kind of a competition between the two of us. It comes back over and over again. But it's based off of Planck's constant. Avogadro's number, which used to be the conversion between the Dalton, which is the unit of mass we use for atoms, and the gram, is now just a number. So it's just a number. Now, it happens to be just a number that happens to be the number as close as we could possibly get it to that conversion in 2019. So Avogadro's number is now the definition of a mole. The ampere is based on the charge of an electron and the number of electrons flowing. The Kelvin is based off of the Boltzmann constant. The Kelvin's based on the Boltzmann constant, and the Candelia is based on luminescent efficiency. Kelvin is temperature. It's an absolute scale, so unlike centigrade, and we will get to Kelvin later on. And the Candelia is brightness, so how bright something is. Okay, so those are your 7 base units. And what you'll notice is we've been changing those based off of some form of natural law. That way, you can't accidentally melt it. Now, that's only 7 units. There's a lot more things to measure than 7 units. And I kind of got into this idea of derived units already. If I want to measure area, I don't need a new unit. I can just do a length squared. If I want to do volume, length cubed. If I want to do, say, concentration, I can do a mass unit and a volume unit. That works. Or I can do a moles per volume unit, the good old molarity. Now, sometimes maybe I want to take a couple of things together. I don't actually want to make myself a new unit. So in that case, I could create what we call a compound unit. So something like density, grams per milliliter. We're taking a volume unit, which is itself a derived unit, and a gram. And of course, I just use milli. Because it turns out we still have that problem with seeds and goats. I don't really want to measure the length of a cell in meters. Meters are relatively large compared to cells. As such, I need to shrink down the meter. Now, the US customary system and the imperial system before that did this by just creating new units. We've got the foot, and we got the yard, and we've got the inch, and this conversion is kind of awkward. We've got 3 feet in a yard, 12 inches in a foot. There's a lot of base 2 going on here. There are reasons that imperial and later the US customary system uses some of these conversions. The inch is roughly a finger, and a foot is a foot, and a yard's a stride. So don't get me wrong, these systems are not nearly as bad as people make them out to be. They're very logical systems, but they're kind of awkward to use, especially now that we've got high precision. So the metric system, the original metric system, came up with a solution, and that was prefixes. We're going to have a series of prefixes that describe a multiple of 10 for that unit. So if I've got my unit, my meter, my gram, my whatever, and if I want 10 of them, I would do deca. If I want 100 of those, I'd do heca. So a hecameter is 100 meters long. Likewise, if I want to go down, I could do a micrometer. That would be 1/1,000,000th of it. Side note on the micro, there's a couple of interesting bits to it. Usually you get a word, like micro, that acts as a prefix, so I'd say micrometer. But I can shorten things. The meter can be shortened to an M, and then the prefix would be shortened to a letter. Now, most of your prefixes are shortened to just a normal letter that we'd use in English. But micro is given the Greek letter mu, lowercase. It kind of looks like a U with a tail in the front. Now, this creates a little bit of a problem if you happen to have bad handwriting, and physicians are known for bad handwriting. That could look like an M if you're really sloppy, and M is another prefix, milli, and that's 1,000 times larger. As such, you could accidentally prescribe 1,000 times too much drug. In the US, physicians don't use micro, they use MC for micro. In the UK, they don't shorten micro at all. It's microgram or microliter. They write out the full word. By the way, how does the non-medical community do it? We type it, or we take our time to write neatly. Like, seriously, this is not that big of a problem. Just type. I don't know why we're handwriting any of this stuff here in 2026 and beyond. Okay, so let's talk briefly about density and actually using numbers in equations. So one of the first things I'm going to have to point out is the units are absolutely critical for numbers. Please don't drop units. We're quite often taught to just use the values and do math on the values and ignore the unit. And partially that's because that's what computers and calculators and other devices need. You don't type in the units into your computer. However, those units provide absolutely critical context. So if you've seen those obnoxious Facebook memes of, what is, 3 times 2 minus 2 kind of things, and everyone argues about the answer. If there were units, you wouldn't be having that argument. Because you would understand why you're doing the math and what the math is. If it's just a bunch of random numbers, well, who cares? It's just a bunch of random numbers. It has no meaning. It has no value at all. And that was, of course, the joke from Hitchhiker's Guide to the Galaxy. 42 means nothing. Well, so the first thing we want to do is keep ourselves some units on there. But also, we can interrogate the units. We can look at the units and not just understand what's going on, but actually understand what we need to do. And the classic case study, the one that most chemistry teachers start out with, is the idea of density, just because it's a nice, easy compound unit to use. And so what we can do is if we know the weight of something and we know its density, we can then calculate its volume. Fairly straightforward. And the way we do that is we look at density, and we look at it as 2 units, a volume unit and a mass unit, and we can use dimensional analysis. Dimensional analysis is looking at the units analyzing them and coming up with an equation to get to the unit we want. So if I have, say, 20 grams of, let's say, gold, I believe gold has a density of 19.3 grams per milliliter. Obviously, it depends on the temperature, depends on pressure, quite a few other things. But we'll just call it 19.3. And so if I have 20 grams of gold, I can divide that by 19.3. Well, if I take a fraction, like the grams over milliliters, and I put that in the denominator of that fraction, it effectively flips up. And so the grams will cancel. The milliliters will become on the top. They'll become part of the numerator now. And as such, I can now take 20 divided by 19.3 and get my answer in milliliters, which will be, what, just slightly over 1. And so this is a very useful technique. We can analyze quite a few things. And this is one of those, if you ever take a chemistry course, you'll spend, for a Gen Chem 1 course, probably the first half of the class, or maybe the second half, depends on how it's being taught, just doing this over and over again, because it's an incredibly valuable technique. You're able to extract information that you wouldn't necessarily think you have just by looking at the units. And so it's one of the reasons we never want to start dropping the units. Because if you say make a mistake, you do 19.3 times 20. Well, if it's 19.3 times 20, I don't know, sounds fine. But if it's 19.3 grams per milliliter times 20 grams, well, now I get some number of grams squared milliliters. What? That don't make lick of sense. And of course, that means that the value doesn't make a lick of sense either. So that gives me a lot of information here. It tells me if I'm doing things right, if it tells me if I'm doing things silly, and then also tells me what I might need to do. So this is a technique called dimensional analysis, incredibly useful technique. Now, we are not perfect. We as humans make mistakes. Everything we do is imperfect. And just like I talked about types of error in logic last time, this time I want to talk about types of error in measurement. When we're measuring something, there are kind of two ways it can go wrong. And by two ways it can go wrong, I mean two ways it will go wrong. You cannot escape this. This will always happen. The only question is how much. The first is what we call random error. And this is every time you measure it, you measure just a little bit differently. There's a little bit of wiggle. You have a slightly different angle on your measuring tool. Thermal expansion causes it to change size just slightly. And so you get a slightly different number. Now, the more careful you are, the better the tools you have, the less random error you have. And having a low random error is something we call precision. Now, what low is depends on what you're doing. For example, if I'm measuring out, say, mashed potatoes, and I give one person a couple of grams extra, the next person a couple grams less, that's not that big of a deal. They're just mashed potatoes. We're only talking maybe a spoonful or two here. However, if I'm distributing, say, gold pellets, and I'm off by a couple of grams for one person, I give another person a few grams of gold less, well, they're probably going to complain a whole lot more being shorted a couple of grams of gold. So all of that we're talking with like high and low precision, that is entirely relative to what you're doing. And this kind of gets into this idea, though, as a society. We've gone from a society where we need relatively low precision to one where you need more and more increased precision. And thus, the progressive technology has been this quest for precision. Now, the alternative to random error is called systematic error. And systematic error is every time you measure it wrong the same way. And this leads to a value that's just wrong. Now, precision is fairly straightforward. You just take a bunch of measurements and you average them out. That'll give you a better answer, and then you can look at that spread, and that will tell you how good your precision is. But if you average out a bunch of errors with systematic error, that doesn't tell you how good it is. And your number is going to be off when we talk about how close you are to the true value as accuracy. Now, technically, the true value is unknowable. If you already knew the true value, then why are you measuring it? But there's a bit of a cheat. Remember those standards? Well, if you measure the standard, or you measure something that's been measured against the standard, well, you're going to make, it's a logical fallacy, but it's as good as you're going to get. I'm going to assume that if I keep everything exactly the same, as close as humanly possible, then the amount of systematic error when I measure that standard is going to be the same as the systematic error when I measure my thing. Now, that's not logically perfect. Those are two different measurements. They could be different, but if I keep everything very close to the same, as close as humanly possible, then I'm going to get as best a description of accuracy as humanly possible. Obviously, we want high accuracy, we want high precision, but it takes more work. And sometimes, well, is the juice worth the squeeze? It depends on what we're doing. Sometimes we put the effort in. It's needed. Other times, we don't care. We do need to communicate, by the way, how much effort we put in. There's several different ways. If you're in a chemistry class, you'll learn a technique called significant figures, which describes how good the numbers are. By the way, accuracy and precision only apply to measured numbers. If it's a definition, we call that an exact number. There's no error in there. It's the definition of it. So there's 1,000 meters in a kilometer by definition. Also, generally speaking, we don't consider counted numbers to have error in them. You could get them wrong, and that's a mistake. That's not an error. Error is imperfection. Just straight out making a mistake is making a mistake. So if you're doing a true count, 1, 2, 3, 4, if there's 5 people in the room, there's not 5.5. If there was 5.5, you'd be calling the cops because you got half a corpse in the room, kind of thing. So measured numbers, which are basically going to be everything. There's always going to be a little bit of error. And basically all we're trying to do is control that error and communicate it. You do significant figures, you can do a standard deviation for precision, you can do propagation of error, which is a somewhat more complicated one. And then when we're graphing it, which is going to be the next thing I want to talk about, you can put on what we call error bars, which shows you your confidence intervals. And there's other mathematical ways of doing it. So, if you've got the bar here, you can say, well, it's good within that much, kind of thing. So you can kind of little feelers on either side of the bar to kind of describe what range you're confident with. And that's important to communicate, because sometimes, well, if things are really close, well, maybe you're seeing something important. Maybe you're seeing just the imperfections in your measurement. And it's important to know, how confident am I in these numbers? Because they're never perfect, ever. Okay, so a couple last little bits. I do want to bring up one term, that's the term significant. I mentioned significant error, or significant figures. The term significant in math and science means that I'm confident the two numbers are different. It doesn't mean it's big. It doesn't mean it's meaningful. It just means I'm confident the two numbers are different. And that can get a little bit of a confusion, especially in newspaper articles, et cetera. It's like, oh, there's a significant impact on cancer by this eating whatever plant. Yeah, it's significant, but it's a very small number. We can measure it. We know it's real, but not enough to care about. Or maybe it is enough to care about, because significant just means we can measure it. Now, when we're talking about data, I want to talk a little bit about graphing, because turning numbers into a visual representation can quite often greatly improve understanding. It's not essential, but quite often we humans, we like visual stuff. The computer can deal with the numbers all day long, but we would like to see some pictures. Generally speaking, in the sciences, we are predominantly going to use one of 3 different types of graphs. I'll start with the least commonly used, and that's the pie chart. One, please don't make it that weird 3D pie chart. You don't need the 3D pie chart under normal circumstances. But this one, you got a circle, and you're going to have wedges, and the size of the wedge represents a percentage. You only do a pie chart if there's a percentage involved. So percent of total of some flavor, or parts of total. Not necessarily percent, but it would still be a percent. The next one we will do is called a bar graph, and or Excel calls these a column graph. The idea here is you've got 2 axes. The x-axis in sciences in general is what we call the independent variable. This is the thing that I controlled. I am influencing the independent variable. And then the y-axis is the dependent variable, and that is dependent on the independent variable. Basically, the y is f of x. And so in a bar graph, the independent variable is just some kind of category. It's not a numerical value, where the dependent value is some kind of numerical value. And so now I have bars that are the height of something. So, I could have, students and then performance on whatever test kind of thing, and I could graph that. And so this way I can look at trends, who did the best, who did the lowest. I can clump them together in different ways and get a general understanding of what's going on. You get in some weird ones where you're doing like months, where it's like, it's not numeric data, but it is numeric data. Now, if my independent variable as well as my dependent variable are both numeric values, I use what's known as an XY scatter plot, or XYZ if I'm doing it in 3 dimensions, because you can do a 2-dimensional graph, but you could do more. In an XY scatter plot, it's the same basic idea, except for the x-axis is a numeric value as well. And so what we're going to create is a bunch of data points. And, a point has 2 numbers, a y value and an x value, and you put them on there. This is not a line graph, by the way. The line graph is always in order, where an XY scatter plot, you place them where the numbers go. You're not trying to put them in a row. So a line graph actually has more in common with a bar graph than it does a scatter plot. Now, if you do the scatter plot, you can then say, okay, hey, computer, or you can do it yourself. I know one person who's done this. You can run the math and you can create what we call a line of best fit, which basically is trying to draw a line through the points. It doesn't connect the dots, but it's trying to draw a line that approximates the pattern the dots have done the best. And with this, you get an equation of the line, which you can then use as a model to predict things. Or alternatively, you can do a goodness of fit. R squared is a popular one. Excel will give that to you. And it basically describes, well, how much of f of x does x describe? How much of the dependent variable is described by the equation and the independent variable? So some very useful tools. You can, say, plug in temperature and figure out ice cream sales or whatever. Okay, so with that said, this is a very brief introduction into metrology and data analysis. There is tomes written on every subset I've talked about, but the video is getting long enough. I've already changed the batteries once, so probably should be wrapping things up. Have a wonderful day, and I will see you in future videos.